Okay, in this video, I'm going to go through some of the chapter review questions for chapter 10. I'm skipping through some of them, which are things you can just kind of read about, or they're very simple calculations. So I'm just going to do more of the problem solving exercises. So let's just get my images in order. So fine, just number one. All right. So in this case, I'm actually going to start with question 5. You can find the chapter review questions in the textbook on page 367. All right, so question 5. Platinum has a threshold frequency of 1.5 times 10 to the 15 hertz. Calculate the maximum kinetic energy in electron volts of the emitted photoelectrons when ultraviolet light with a frequency of 2.2 times 10 to the 15 hertz shines upon it. Okay, so the strategy I used here, I started with the threshold frequency and I went to find the work function. So, okay, by the work function is equal to Planck's constant time by the threshold frequency. So this will give the photon energy, which would be just enough to release a electron. All right. So calculating that, I ended up with approximately 9.9 times 10 to the minus 19 joules. Let's move it across a bit more so you can see the whole thing. All right. And then I went to find the maximum kinetic energy of the photoelectrons if we would shine a light with frequency 2.2 times 10 to 15 hertz using the maximum kinetic energy formula, photon energy take work function. So HF, H times F, minus work function, you end up with 4.6 times 10 to the minus 19 joules. Now I actually forgot to convert that into electron volts, which is easy enough to do. Just take that number and divide by, so 1.4 times divided by 1.6. So 4.6 times 10 to the minus 19 divided by 1.6 times 10 to the minus 19 will give you approximately 2.9 electron volts to two separate figures. All right. So that is question 5. All right. So question 6 I'm going to do here. All right. This is probably might be one of the easiest questions in the book. The stopping voltage obtained using a particular photocell is 1.95 volts. Determine the maximum kinetic energy of the photoelectrons in electron volts. Well, that would be 1.95 electron volts. That's it. Because remembering the stopping voltage is what stops all the photoelectrons, so there's none coming through, there's no current going through the multiply tube. Thereby, that much energy can be expressed, and because we're using the energy, the voltage is stopping electrons, so thereby the energy, the magnitude of the energy is the same as the voltage. We just say it's 1.95 electron volts. All right, question 7. You can pretty much just do this by reading off the graph. From the graph, determine the value of the work function metals for each of the metals. All right. So you can look closer if you want to. If you had a digital copy, you can kind of enlarge it and maybe just get a ruler out so you can get a little bit more accuracy. But if we were to do this, rubidium. Okay, so at that point here, so the blue line rubidium, I think it's rubidium. Okay, that line here, this horizontal line is 2.5 in the negative, so 2.5 work function. So about in the middle, you could say that's 2.25. So I would guesstimate that to be about 2.2 electron volts. Sr, so strontium, is 2.5. Magnesium is close to 3.5. You could say 3.4. I would accept that. And W is tungsten. That would be 4.5. Okay. So, okay, I'm going to do question 8 as well. The cathode of a particular photocell shown below is coated rubidium. Incident light of varying frequencies directed onto the cathode cells of the cell, and the maximum kinetic energy of the electron is logged. Okay. The results are summarized in the following table. Okay. So we've gone and done the experiment to measure the maximum kinetic energy. All right, and you've got the table here, and we have to answer some questions based on that. So we've got to plot the graph, plot the points from the table onto a graph, calculate the gradient of the graph. Based on the graph, experiment results with the threshold frequency of rubidium, will red light of 680 nanometers cause photoelectrons emitted from the rubidium surface? All right, now I'm just going to close this down because I've actually gone and done this. I decided to do this in Google Sheets. Now, for the sake, because you actually need the slope, just to make things easier, I've just gone back to graphing. I actually put my data table in. So I took the times 10 to the 14 and actually put this into the scale. So into here instead of into there. So this frequency in hertz is not frequency in hertz times 10 to the 14. So that way I don't have to worry about scaling when it comes to my values here or here. So frequency is frequency. There's your electron volts. And so I've graphed this as a scatter plot. Kmax and frequency, and here's a graph. I've actually scaled it so I have the origin included as well. So the slope, I'll bring up my notes here. All right, so I've got it to do find the linear expression for this. Now remember, in the equation, if you graph in electron volts, I prefer this equation, EK max equals H divided by E times F take W. Whereas in joules is H times F minus W. Now I use H on E because I'm still using the Planck's constant, which is in joule seconds. When that's divided by E, then it becomes in, it's the Planck's constant for electron volts. But, so I managed to get the slope of, I've written down, bring that across more. I've written down the equation from sheets here. So EK max equals 4.4 times 10 to the minus 15 frequency. That's what actually is graphed on the x-axis. So change that to NF minus 2.07. All right. So the slope of the graph is 4.14 times 10 to the minus 15 electron volts. If you want to kind of use that to work out Planck's constant, you don't have to, but it's out of curiosity to see what it looks like. If you times by charge of electron, 1.6 times 10 to the minus 19, you get 6.624 times 10 to the minus 34. So you're pretty close to Planck's constant. Corrected to some figures anyway. Now you can get the work function from the y-intercept, as we did in the previous question. And I'm going to convert that to joules for this question. All right, so I'm actually working out the threshold frequency. All right, so working that in joules and then divided by Planck's constant, I can work out the threshold frequency, which the 2 cent figures is about 5.0 times 10 to the 14 hertz. Now the final question, will this wavelength cause photoelectric effect? Well, let's look at its frequency, and we'll draw a comparison with the threshold. Well, the frequency is speed of light divided by wavelength, so working that out, you end up with 4.4 times 10 to the 14. I forgot to write hertz at the end there. Okay, now this frequency is smaller than the threshold frequency, so no photoelectric effect, no electrons will be formed as a result of this because the frequency is not high enough. The photon energy is not high enough to overcome the work function. So that is the first page of questions. So I'm going to close this, and I'm going to close that, and I'm going to look at my second one. All right, so let's have a look. I'll close you too while we had it. All right, so let's look at the second lot of questions. The first one was a lot to do about photoelectric effect. These ones have a bit more to do with atomic energy levels. So, all right. So, all right. So I've picked a few. Let's go through question 11. Which of the following would have the longest wavelength? And they've got a few different particles and photons there. So electron, proton, X-ray, and blue light. Now, blue light and X-rays are both classified as photons. So if I'm wanting to establish which has the longest wavelength, I straight away crossed out X-rays because visible light has a longer wavelength than X-rays and gamma rays, so and ultraviolet. So just by awareness of your regions of the electromagnetic spectrum, blue light would definitely have a longer wavelength than an X-ray. So I cross out X-rays without bothering to even convert it. If you want to, you'd find it's probably within somewhere between 10 to the minus 9 to 10 to minus 11 meters is the typical X-ray wavelength range, and well, sometimes a bit more, so a bit smaller. Okay, so I have done the calculations for the other ones though. So, all right, so electron, well, we got something that's comparable to an X-ray. Proton, we got something even smaller. Let's see here. So blue light's our winner, so I circled B. Okay, so for question 12, what is the de Broglie wavelength of the 40-gram bullet traveling at 1 times 10 to the 1,000, 10 to the 3 meters per second? Okay, so putting that into calculation, you end up with this number, 1.66 times 10 to the minus 35 meters. And the following question for that, there's no wave behavior because this is actually far too small to observe wave behavior. We've talked about where like X-rays and electrons being diffracted by the interatomic spacing of crystals, and those are on interatomic spacings are the order of 10 to minus 10 to 10 to minus 12 at the smallest, and then you go down a couple more orders of magnitude. 10 to the minus 14. You're talking about the spacing of nucleons in the nucleus. 10 to the minus 35, that's nonsense. And also, yeah, basically the bullet wouldn't even fit. Yeah, so this is kind of, you can do calculations of Broglie wavelength for all sorts of things. Do they actually mean anything? In this case, no. This is a kind of a meaningless tiny value. So far too small. It needs to be, if it's going to be wave effects, particularly something like diffraction, there needs to be there's something that scales of the order of the wavelength of whatever we're dealing with, and it's not the case here. Okay, so it's not possible. Nothing's that small. Okay, calculate the frequency. So now this is actually, there's not too many kind of problem-solving questions in terms of emissions, but I've done one here. Okay, so calculate the frequency of the photon produced when an electron in a hydrogen atom drops from the N3 level to its ground state, N1. Okay. All right. So I got this off. I'm not sure. I didn't actually use the figure they cited, but I just pulled another one off. The values are similar. If anything, they're probably they've got extra snippet figures. So these were actually given. The values I've got here are the bound energy state. So the ground state, the electron is bound with 13.59 electron volts. That means that's how much energy is actually required to liberate it from that position. And then 2 energy levels above that, I've found that it has a bound state of 1.51. If you just work out the difference, you can find the energy of that transition, and it's 12.08 electron volts. I'm going to multiply that by charge of electron to get it into joules. So there you go, 1.93 times 10 to the minus 18 joules for the photon energy. And then, okay, we have to work out the frequency. All right, so let's divide by Planck's constant. All right, so 1.93, 10 to the minus 18 divided by Planck's constant, you end up with 2.92 times 10 to the 15. That's close to visible, but no, it's actually 10 to the 14, typically visible. This is actually ultraviolet. Yeah, you can also recognize visible from the types of photon energies when you've done enough of these questions. And this is in the ultraviolet. Okay. So, yeah, that's all I wanted to go through as far as these. If you have any questions, please feel free to contact me.